Problem 29, I'm going to show you how to derive a formula which you will subsequently use in other problems. That formula is to figure out velocities of objects after an elastic collision. You do not have to perform those manipulations in the subsequent problems, but you do need to understand it, so do take time to understand this. We have an elastic collision, so it's stated right here, which will obviously never happen in real life because we have two cars colliding, one of them, and they're real cars. So we have a van which was at rest in the beginning and a 715 kilogram car. The initial velocity of the car is 225, and they give you a plus to say that it's forward, to the right, whatever. We need to figure out the final velocity of the car and the van. Or I know that my momentum is conserved and it's elastic collision, therefore I know that my kinetic energy is conserved. Initial momentum and kinetic energy for the van was 0 because it was at rest. Conservation of momentum. This is my initial momentum for the entire system because there's only one car moving. The momentum final is right here. It's two cars moving. Since the van is so much more massive and it's moving obviously forward from real life, you can imagine what's going on. It's going to move forward. And since this guy is about half the mass of the van, it's going to bounce backwards. So you can expect the final velocity for the car to be negative, which you will see. Right now, what I have is one equation. These two are numbers, so they are known. But then I have one variable and another variable. Two variables with one equation you cannot solve. In order to be able to figure out both velocities, I need to bring up another equation, and that would be conservation of kinetic energy. Again, this right here is the initial kinetic energy for just one car, and that's my final kinetic energy. Both objects are going to be moving. The energy is conserved because it is elastic. Here is where physics ends. That's it. After this, it's just algebra. First thing, I'm going to multiply by 2, get rid of 2 here. So that's what my conservation of kinetic energy turned into. Got rid of 2's. Then what I'm going to see is I have mass of the car, and mass of the van. So what I'm going to do, I'm going to divide by mass of the car. So I'm going to have mass of the car goes, and here I have mass of the car going in the denominator under mass of the van. Now what I'm going to do, I'm going to rearrange this and put this part on the left with a minus, and just to rewrite this as velocity final for the car equals velocity initial for the car minus mv over mc, and that's v final for the van. I'm still stuck with two variables. I don't know what this is and I do not know what this is. So what I'm going to do, I'm going to get rid of velocity for the van. And in order to do that, I'm going to go back to my conservation of momentum. Got rid of 0, so that's initial momentum of the system, that's final momentum of the system. I need to substitute for velocity final of the van. Then I have both velocities multiplied by the mass of the car, so I'm putting it in front of the parentheses. And then to figure out just the velocity, I'm going to divide by mass of the van, and this is what I end up with. So velocity final of the van, mass of the car over mass of the van, and the difference between initial velocity of the car and final velocity of the car. So what I'm going to do after that, I'm going to take this and put it in here. I'm going to look at this equation right here and put this, which I got from conservation of momentum, instead of v final for the van. This part is the way it was. Then I have the ratio of masses, which was intact. We kept it. And then instead of v final of the van, I'm plugging in this formula right here. So I have the ratio of the mass flipped, squared, and then square of the difference of velocities. Since this is squared, I can take the square out and take these masses out. And so what I end up with is this. So my ratio of masses just flipped. And what I also did is I took this, put it on the other side of this right here. I put it on the other side of the equation sign, so therefore it became minus. And then I'm going to look at, this is the difference of squares. And as you remember, the difference of squares is the difference times the sum. If you look into the brackets, velocities of the car in both cases. So I can basically take this out and this out, and I will end up with this. Okay, so take a breath, look through this. If every step makes sense, we just substituted, and then foiled, unfoiled, whatever you want to call it. In order to get rid of this ratio of masses, I'm just going to multiply everything by mass of the van and also distribute this right part. Hence, appears here and disappears on the right. And I also distributed this. Rearrange this. I have velocity of the car final here with a plus and velocity of the car final here but with a minus. So I'm going to put it on the other side of the equation with a plus. Hence I ended up with this. And then this right here is my initial velocity of the car. I'm going to put it on the other side again with a minus. So now I have final velocity of the car, final velocity of the car, and then initial velocity of the car and initial velocity of the car. I have the sum of masses on the left and the subtraction or the difference of masses on the right. And this obviously is a positive number, but this will be a negative number because your van is so much more massive. And remember I told you that most likely the car is going to bounce back because the car is not as massive as the van. If it was the other way around, if the van ran into the car, then obviously it would just plow forward and the car would be pushed forward very fast. Right now, since I do know this initial velocity of the car and know both masses, I'm just going to divide the right side by the sum of masses. So we have that formula and I can figure out the velocity of the car using this formula. So 715 was the mass of the car, 1055 was the mass of the van, the difference over the addition, 225 was initial velocity of the car, so I end up with negative because the car bounces back. And then this came from the conservation of momentum. I'm subtracting the final velocity of the car, and the final velocity of the car is negative. It ends up to be a positive number, and so the van is going forward much slower, because remember, the car itself, when it just bumped into it, was going 225. So it pushes, gives some of its momentum to the van, and the van is so much more massive. So if I take 715 times 225, which was my initial momentum, 1055 times 182, which is the final momentum of the van, indeed this final momentum of the van is greater than initial momentum of the car. And they were both to the right. This guy is going right, and that guy's going right. So since this one, the final, is greater than initial, then obviously I will have to have my final momentum of the car directed to the left. Hence your negative velocity right here.